Yes, it has started recording, so please type in the chat your name followed by the statement that you were present. Okay. So hopefully you can also see the screen, and then by the way, so we will be sharing these recordings in this Google Classroom in the appropriate place. So if any one of you need to revisit those things, you can do that in Google Classroom. Okay. So today we will continue with this theory of probabilities, and yesterday we discussed the shortcomings of the frequentist approach to probability. So we have discussed like the shortcomings of the classical definition of probability. So we have discussed this, and now we will move beyond. And today we will discuss probability as an abstract concept, and then this was given by this person called Kolmogorov. So today we will start with the uh, Kolmogorov definition of probability. Right. So, to start with, first of all, we will consider a set that is kind of the which contains everything. It's kind of the universal set of everything, and we call that set sample space. So, first we define a set S, which is called the sample space. Yeah. And this is a set containing a certain number of elements. Okay, so the interpretation of these elements are left open for the moment. Okay, so we do not say what these elements are. These can be anything, but for now, this space is a set containing certain number of elements. It's okay. Now, so we will define. So there are many subsets of this S. So to each subset A of S, uh, we assign a real number that is denoted by P of A, uh, and we call uh, probability. And having the well, following properties. So to each subset A of S, we first assign a real number PA. We call that real number the probability pertaining to that subset A, and it should have the following properties. And the properties we will now list down. So first property is that for every subset A of S, uh, P of A should be greater than equals to 0. So this should be a positive number, a positive real number, This is the first thing. And then for two independent subsets, say A and B, uh, this independence means that there are no common elements of A and B. That means this, if you take the intersection of A and B, you will get the null set. Okay. So this is the null set. So for two independent elements A and B, such that A intersection B is null set, uh, the probability of A union B, probability of A union B is just the probability of A plus probability of B. Okay, so these are the things that you should remember. That these are the axioms. First of all, we don't prove these. We just, in this abstract formalism of set theory, we just define probability by these properties. Okay. So then, the third property is that the total probability is one. So the probability corresponding to this total set S is equals to 1. Okay, so this automatically guarantees that all the probability are greater than 0 and less than 1. So if you take this into account, so since the probability is greater than 0 and probability of union of two sets, okay, should be the sum of the individual probabilities. uh, you have a doubt? Okay, tell me, what is the doubt?
Sir, why there is two independent subset? Is it disjoint subset?
Yes, these are disjoint subsets basically.
Why is it always necessary that we consider two independent subsets?
Yes, for this to hold, for this rule to hold,
Actually, is it only the disjoint subset we consider only?
yes. So I am now defining probability first of all. So these are the axioms of Kolmogorov, and
Okay,
from these we will derive the condition if A and B are not disjoint, then what will happen? That will come in for the conditional probability part.
okay, sir.
Okay. So these are the basic definitions. So these are basically, if you like, these are Kolmogorov's axiom. Okay, and so the total probability is one. So this these three together ensures that the probability should lie between 0 and 1. And so these three together. Now there is a fourth axiom. This fourth axiom we actually proved yesterday in the frequentist approach of probability. But in this abstract formalism, there is no way to prove it, and that's why we just introduce it as an axiom. That's the rule for conditional probability. So we just define that. So suppose again A and V are subsets of S, but this time I do not say anything about their independence or whatever. And we also assume that P of B is not equals to 0, that is, B is not a null set. Okay. And then the conditional probability uh, that P of A given B uh, should be equals to P of A intersection B divided by PB. So yesterday we actually made sense of how this comes into being, but that is in the frequentist approach. But in this more formal definition, this comes as the fourth axiom. So this is as comes as the fourth axiom. We don't prove it, but this is my axiom. Starting from so with these four axioms on probability, we will start looking into things, and we will do more involved things. Anyway, so the first thing to notice, of course, is that if this B is equals to S, so suppose if you replace B by the total set S, then it certainly makes sense. So then P of A given S, since S is my total set, and this is equivalent to P of A intersection S, which is just P of A, because that's the A, and P of S is 1 according to my axiom. Okay, so if you so this is what you would expect normally, and so probability of A can be regarded as the probability of A given the total set S. Okay. Now, one immediate consequence from this one, if you remember that P of A intersection B is equals P of B intersection A, because this intersection operation commutes between two sets. And then if you interchange A and B in the other parts, then what you get is that you get that P of A intersection, sorry, A given B should be equals to P of B given A times P of A divided by P of B. Okay. So just to do the algebra simple. So this is basically the statement of Bayes theorem that we came across yesterday. Okay, and this is kind of the bedrock of what we will do in data analysis, and how we will do that. This forms the bedrock for that. All right. Now we need to cast the Bayes theorem in a bit more of an usual form, or more useful form. So now we will take this Bayes theorem into, say, more useful form uh, that we can recognize, and we can deal with. Okay. So how to do that is, what we do is that we divide the total set S into a number of subset that kind of constitutes my whole sample space. Okay. So first, diagrammatically, if I kind of draw a simple Venn diagram like thing, then it should look like this. Suppose this is my set S, and inside this set, this is, say, let me draw inside something. This is my, say, B, the set B. And first of all, let me subdivide this S into a number of subsets. Okay, so let me put like, so, oops. Okay, so these are different. These dotted lines are. So suppose this one is A1, this one is A2. I divide this thing, and suppose this one I called AI, the ith A. Okay, so basically, I have rewritten the total set S as the union of these AIs, and I noticed that all the AIs are kind of independent. That there are no overlap between any two AI. So if you take the intersection operation, you will get the null set. Okay. Now I also noticed then in this. in this operation, because of this operation, I can think of B to be composed of some small parts. So suppose, so this is kind of so this part is AI intersection B, and B can be thought of to be made up of all these kind of pink segments. Okay, so this one will be A1 intersection B, and so on. So B can be thought to be composed of these pieces. So you can write that my B is basically the union of AI intersection B. Okay, so this will give me my total B. Okay, and so then if all these things are disjoint, then I can write then the probability of B, which is then the probability of union of AI intersection B. Let me put another bracket here. Okay. Now, remember from my second or third axiom that the union of two independent sets are the sum of those sets, sum of the probabilities of corresponding to those sets. So again, then so this one I can usually write as the sum of the probabilities of those individual intersections. So AI intersection B. Okay. Now, this, according to the rule of compound probability, conditional probabilities, actually, so P of A intersection B is P of A given B times PB. So from this, I can, from that axiom, I can write. So this is that my summation over I. So P of, I am just reversing this one, B given AI times P of AI. All right. So the total probability of having B is that P of, if I subdivide the total sample space into say n subsets, which I call AI and so on, like convenient subsets. So what convenient subsets I mean? I'll be giving an example, and that will illustrate the problem. So P of B is given by this one. So now if I substitute this formula in the West theorem, so P of A given B was P of B given A times P of A divided by summation over I P of B given AI times P of AI. So you, if you notice carefully, so this one in the denominator is just PB. So this is the rewriting of PB, and AI basically a convenient decomposition of this total sample space into n pieces, such that I can find the compound probabilities quite easily, or the conditional probabilities quite easily. Okay, so let me give you an example such that to illustrate these points. So let me put an example now. Okay, so suppose there is a disease that is carried on by 2.1% of the population. So suppose there is a disease which is known to be somehow, disease known to be affecting, say, 0.1% of the population. Okay, and then there is a test that has been designed to check whether you have the disease or not. So suppose there is a test for that disease. So test for that disease, and the statistics for the test is something like this, that it is say 98% accurate if the person carries the disease. So suppose, let me put it that 90.8% uh, accurate when accurately determines when someone carries the disease. Okay. So what I mean is that, so you have either the disease or you don't have the disease. So I mean that the probability that the test will give you positive result given you have the disease. Okay, so that is the probability that is to test positive given that you have the disease is 98%. So this is 0.98. Okay, but the test is not perfect. That's why the test might give you negative results even when you have the disease, and the chance for that is only 2%. So it's fairly accurate. And if you do the test in the other way, suppose the test is also faulty in the sense that it sometimes gives you false positive. So okay. So chance for false positive is 3%. Let's say. So it has a 3% chance of giving you false positive result. That means the probability of testing positive if you don't have the disease, so no disease, okay, this is 0.03, and probability of testing negative if you have no disease, uh, since the test is fairly accurate, so it's 97%. Now the question is, given all these information, uh, suppose you undergo a test. Okay. So now the question is that someone uh, undergoes the test and the result is positive. Because this is the case. Then I want to ask, then what is the actual probability? So what is the probability that the person has the disease? So now, if you are kind of not trained in statistics prior to this, then perhaps you will like assume that since the test is pretty accurate, if I test positive, it's bad news for me actually. So, but you will see that it is not the case, and the key factor is that the disease is rare. Disease is 0.1%. Okay, and so let us first write down what we want. So we know all this data. So now I want to know that what is the probability that I actually have the disease given the information that I have tested positive. Okay, so this is what I want, and I know all these informations. So in terms of this, I have to now calculate this one. So now the Bayes theorem basically comes into my help. Okay, so I will use now Bayes theorem to actually determine what is the chance that I actually got the disease. So probability of having the disease when you test positive, you can first of all you notice that the p of A given B is related to p of B given A, right, times PA. So first, let me write that down. So it basically reverses the conditional probability. That's it's a powerful thing. So it relates that P of testing positive, given you have the disease, and probability for having the disease itself. Okay. So that is P of B given A, and that is the probability for the disease itself. Okay. And then divided by, you have to find P of B. Okay. So P of B, so B is what event? So B is testing positive. So divided by the probability of testing positive. Okay. Now how do you determine this thing, the probability of testing positive? Okay. That's where this formula kind of comes into your records. So this is P of B, and the total set is subdivided into convenient subsets. So how can you test positive? So when can you test positive? You can test positive if you have the disease for sure, and you can also test positive even if you don't have the disease. Okay, so there can be true positive plus false positive. There are both chances. Okay, so this probability of testing positive is broken down into two parts. Okay, so if you so this AI, now will run from 1 to 2. So either you have the disease or you don't have the disease times P of AI. Okay, so let me write it down. So the P of testing positive will be uh, P of testing positive given you have the disease times the probability that you actually have the disease. And the second term, let me write it in a different color. So this is P of testing positive even if you don't have the disease times probability of having no disease at all. All right. So now I have subdivided these. So this will be this plus this one according to this rule that I have laid down. And if I now plug in all the numbers, actually, so P of testing positive, if I have the disease, that was 98%, and the probability of having the disease was 0.1%, so 0.001, and divided by these numbers. You can check it from what I have written here. This is again 98% times 0.001 plus probability of testing false positive was 3% times the probability of having no disease is basically quite large. So this is 0.999. So 1 minus 0.1% is 99.9%. So if you crank up these numbers, then you get approximately 0.032, and that is 3.2%. So you notice that even if you test positive for this uh, disease, since the disease is extremely rare, there is actually a 3.2% chance that you really got the disease, you are really infected by the disease. Okay, and that has to do with the fact that the disease itself is super rare. Okay, so how to make sense of that? To make sense of that, consider that there are 1,000 people. Okay. So let me suppose there are this kind of 1,000 people. Okay, love. So suppose I have a sample of 1,000 people. And since the disease is the probability that there is a disease is 0.1%, that is, it affects 1% of the population, then I can expect that at an average, out of this 1,000 people, only one person is affected. So this guy is affected. Okay. So now, if you run the test on these 1,000 people, okay, then if the test is ideal, if the test is ideally 100% accurate, then uh, it will only detect this one to be positive and no one else. Okay. So since the test is fairly accurate, I can expect that this one will test positive, but the test can also give false positives. That is, it will give positive results when the person does not actually have the disease. So out of these 1,000 people, since the probability for that is 3%, then out of the rest of the 999 people, so 999 say healthy people, even if you run the test on them, you will see that the around 30 will come out to be positive. Okay, because the test is not perfect. That's the thing. Okay, so you see, if you run the test on this 100 population, total 31 people will test positive, among which only one is affected. Okay? And one is actually affected. So even if you test positive, you are among these 31 people, among which one is affected. So your chance of actually being affected truly is 1 by 31, okay, which comes out to be around 3%, I guess. Okay. Now, so this is the reason, because the test is the disease is itself very rare, and the test that we have designed is not perfect one. A combination of these basically tells you the chance that you actually got the disease is low. But now the question is, suppose you run the test again and you again test positive, then what is the chance that you actually got the disease? That means I'm now asking, what is the chance that the test was wrong twice? Okay, or and the chances are very low. Why the chances are very low? So once you run the test for the second time, you have to update the prior probability. So this probability, now you have a 3.2% chance that you got the disease. So previously you were replacing for this 0.001. If you run the test for the second time, then you have to replace it by 0.03. You have to update the chance that you actually have the disease because you have already tested positive. To why that is true? Because since if you test positive and you run the test again, then you are testing again these 31 people, and now the chance that the test will make a mistake is relatively small. So now you will have a fair chance of actually, if you test positive again, you can say with a fair degree of certainty that you got the disease. You can crank out the numbers, and the numbers will shoot up from 3% to more than 60%, I guess. Okay. You can try that at home. So this is what Bayes theorem can do in practical scenario, like when you need to devise a test and try to you have to design a social protocol based on your statistical results. Then this is how you should think basically in terms of statistics. But the way we will use this Bayes theorem is a bit different from these traditional applications in social science or these medical tests and so on. So you remember that our ultimate goal is to, given a theory and given a data, we need to know uh, how much the data is compatible with the given theory. Okay. So our goal is to know that how much the data is compatible to a given theory. Okay. So what you actually need to find out is that probability of a theory being true given the data that you observe. Okay. So this probability of theory given the data that you observe. Okay. And that, according to the Bayes theorem, so I will be very naive here, but according to the Bayes theorem, this is uh, P of data given the theory is true times the probability of the theory being true, okay, and divided by the probability for data. That means what is the chance that you will observe the data as you have observed in experiment. Okay, so what is the chance for that itself if all the theories were present or without paying any attention to the which theory particularly like. So, so this is the thing. So, first of all, you should notice that this thing in the denominator, it does not depend on the theory at all. Okay. So it is just the probability for observing data. So we can take it out as a factor that does not affect my theory. Okay. So usually, the more usual problems are that these theories are characterized by certain parameters. So that I will denote by theta, and this theta can be anything. Suppose you are doing an experiment with gravity, and you have to fit the data for so the gravitational acceleration without any bias. Okay, and so what is the value of gravitational acceleration that best fits the data? Suppose you are doing the oscillation of a pendulum, and then you have to find the gravitational acceleration by that experiment. Okay, uh, so this type of thing that you have observed the data, then what is the probability for a certain value of theta given the data? So this kind of so the thing on the left is called the posterior probability. Yeah. So this is the thing of importance. So you have observed the data. You want to know. So you want to maximize that. So somehow you want to maximize that. So you want to know for which value of theta, if I observe the data, whatever data I have observed, the probability of theta given the data should be maximum, so that I can say this is my most likely value of theta. Okay. So this is the most likely value of my parameter. So I want to know that. So I want to maximize the posterior probability. And so that is related to something called, if you're if I give you the value of particular value of theta, then how likely it is that you will observe the data as you have. So this is the kind of the inverse of, no, not the inverse actually, it's the opposite, it is the dual of this one. So given the theory, given the value of theta, what is the probability that you will observe the data as you have observed in your experiment? So this thing is called the likelihood. Uh, okay. So how likely are you to observe the data given a particular value of the parameters in your theory? And this is something that is really dicey in Bayesian statistics, and there is a lot of debate, I guess. I mean, I am not a statistician by training, so I do this from practical purposes. So this is the probability of the theory itself. So suppose you are choosing a value for the parameter theta. Suppose you are choosing value for the parameter theta equals 2.3. You have to tell me what is the probability of getting theta equals 2.3. Now, how do you know that? I mean, you know. So for you, theta is an unknown parameter. So how can you know before doing an experiment that what particular value of theta nature is inclined towards? Okay. So this is something that we do not know, and we usually had to put in some assumption somewhere. Okay, so this is sometimes referred to as pi theta, and it's called the prior probability. Okay, so this reflects your belief in the theory, your belief in that particular value of theta before you do an experiment. Okay. Now, how to choose that? How to choose the proper prior? I mean, I will not go into the details because it is, I guess, it's beyond my expertise how to conveniently or how to consistently choose a prior. But one easy way out of this dilemma will be that we use an uniform prior so that we do not show any bias towards any value of theta. So before doing the experiment, we should not be biased towards any value of theta. So we basically choose kind of an uniform prior. Okay. So if you if I try to plot the probabilities for every value of theta, I am plotting a constant function over the physical ranges of theta, and that kind of makes me guilt free that I am not biased towards a particular value of theta before doing the experiment. But this solution is not a very good solution. Let me tell you why. First of all, suppose you are measuring the gravitational acceleration of a planet. I mean, this gravitational acceleration can range from 0 to infinity, but you do not actually believe that it will be as extreme as zero, as extreme as infinity. Okay, so it will be some in between somewhere. Now, where this somewhere is, if you don't do an experiment, you don't have any idea. Okay, that is one thing. But the more problematic criticism is if you choose a uniform prior in say theta. So if suppose pi theta is kind of constant in the range of theta, I will come to that when we talk about the change of variables. But someone, if they change the variable, if they suppose he says that I do not like this variable theta, so instead what I will do, I will parameterize everything in terms of cosine theta, so the cosine of that theta. Okay, so a prior that was uniform with respect to the variable theta is no longer uniform with respect to the cos theta variable. It will do some funny things like that. Okay, so even choosing a uniform prior does not help you to get rid of this problem that when you use Bayesian statistics to get an inference, to get a decision on your theory, you need to specify your prior belief in the theory. And I guess so that is one of the how can I say it? But that is one of the shortcomings of this analysis, and there are methods to improve that. But usually we do it away with the prior probability being uniform, and if we somehow assume that this prior probability is more or less uniform over the ranges of theta that I am interested in, then this the only thing that actually is sensitive to theta is this one. Okay, is the likelihood function. Okay, so maximizing the posterior probability on the left hand side, the maximizing the posterior probability is sometimes synonymous to maximizing the likelihood function. Okay, so if I maximize the likelihood function, then and the value of theta that maximizes the likelihood function will be the most probable value of theta, and we just base our inference, base our conclusion based on maximum likelihood. Sometimes I will come to that in the later part of the course, but this is to give you a quick flash of what will be there to come, and how will you draw conclusions from experiments, and when we have to interpret data in basically in the physics context, how will we use that? Okay, so with that I will I guess stop today's lecture. So only kind of 5 minutes left of the scheduled time. So tell me if you have questions, and we can have a discussion now. Although the class is for 50 minutes, I can continue probably on say 10 more minutes. Uh, I don't know. First, let me see if you have questions. Then I will decide whether to continue or not. Okay. So judging by your silence, then I assume that there are no more questions. So is it okay? Although the class is scheduled for 50 minutes, is it okay if I take a few more minutes? Is it okay with everybody?
Yes, sir.
Okay. Good. So let me continue because uh, yeah, then I will be finishing the syllabus earlier, and I will go get to the important part even earlier. So now I will talk about something that you might already know about it. It's called the probability density function. So, before introducing probability density functions formally, I should talk about random variable and probability mass functions. So, there are two things that I'm skipping here. So, there are two things that I'm skipping, and I am kind of assuming that you have an intuitive understanding of what random variables are, and what is probability mass function. So, probability mass function, that's right, PMF. PMF, I guess it's called. And the PDF, the probability distribution function, PDF is basically the continuous version of probability mass function. So what this idea is essentially about is that suppose if you have a random variable means the outcome of a random experiment you characterize by a random variable. The classic example will be suppose you have if you have a radioactive decay. Yeah, suppose you have a uh, radioactive decay, and it is emitting some alpha particles or something, and you have a detector, and so detector, suppose a GM counter. People who are not from physics background, this is called a Geiger-Müller counter, and it detects radioactive particles as it comes into being, and it counts how many radioactive particles are coming in a given time. And suppose if you have set the timer for 2 minutes, okay, so this Geiger-Müller counter is counting particles, number of particles that is coming into its chamber every 2 minutes. Now, this is a random process. This radioactive decay, it's a random process. So this number that it counts, that is coming into the detector every 2 minutes, is a random number, and it's kind of a random variable. Okay, so and you can assign probability to each of this number. Okay, so suppose you can try to draw a plot. uh, so suppose this is the your count n. So this is I call it count, that the number is that is coming in every 2 minutes, and the this is the probability for n. Okay, so depending on this radioactive substance that is emitting my alpha or beta particle, I can, if I observe it for long enough, then I can assign probabilities to get zero count. So zero probability to get no count in 2 minutes, that no particle enters, it has a certain probability. So suppose I buy a bar. Okay. So this is my n equals 0. Okay. And then the probability for observing n equals 1 count is something like this. Okay. So all the height of the bar is always less than 1 because it's a probability. And this is n equals 1, and this is say n equals 2, and say n equals 3, and so you now get the idea. So what will happen? Okay. And so this is different values of n now. And it is, so this is the typical probability. And you can say that the most likely thing that you will have is either 2 or 3 events to reach the detector. Now, this kind of statement, so by this neat figure, you have kind of conveniently represented this random experiment. So, if you do this random experiment, what is the probability of getting different counts into the Geiger-Müller counter? So, thing on the x-axis is the representation of your random variable that I was talking about. Okay, and this statement of so this plot is a statement of how likely you are, or what is the probability of getting a particular value of the random variable, and this statement is called the probability distribution. Okay, so the statement that gives you the probability distribution is called the probability distribution function. Okay, and if it is a discrete one, technically it is called probability mass function. And if these numbers are very large and these are very close together, then I can think about it as a continuum of random variable, and I will call it a probability distribution function. Okay, so sorry, a probability density function. But in physics, in this language of physics, I will always talk about probability density function, even if I talk about discrete random variables. And if I talk about discrete random variables, for you who are really picky about the terminology, you understand that I am talking about probability mass function. But when I do things in physics, it's seldom important to make a distinction between probability mass function and probability density function. So I will call everything as probability density function. So by probability density function, I mean is that the continuous version of this. So the usual representation of probability density function is the so suppose instead of n, I call it x. This x can represent anything, any random event, and this will be on the x-axis. I call it a function of fx. Okay, and over the ranges of x, depending on which variable you are wanting. So suppose that
Excuse me, sir.
yes.
Sir, I have to attend the class in my discipline. So can I leave the meeting?
Okay, okay. So if you have a class, then I will not continue. Okay, I should not continue. Then you should tell me whenever. So if you have a class, then I will
Yes,
stop
sir.
here.
I have a class from 3 p.m.
Yes, yes, I
So
understand. I understand. So I will stop here because that will not be good to continue. So you are formally registered for the course, this course,
yes,
right?
yes, sir.
Okay. Then I will not continue beyond this point. I will carry it over tomorrow. Okay, so I will end the class here. Is there any questions at this point?
No, sir.
Okay. Okay then. Then I will stop recording, and I will see you tomorrow.